Castro, pode começar.
Ótimo, muito obrigado, Betty. Ok, ah, ok. Bom dia a todos. É um grande prazer estar aqui na defesa de doutorado do Thales, aqui no CBPF. Como temos uma audiência internacional e também um coordenador estrangeiro, eu vou continuar em inglês, tá bom? Good morning, good afternoon, everyone. It's a pleasure for me to welcome you all to the PhD defense of Thales here at CPF. As his co-supervisor, I had the privilege to follow Thales' journey closely, and over the past years, just a few words about his journey. Over the past few years, he faced some unexpected turns. The original research direction had to be changed for reasons outside of our control, and the new topic demanded mastering an entirely different set of tools and methods. But fortunately, Thales didn't let that stop him. He tackled all the challenges with determination and curiosity, and he was very professional about it. He moved into a complex analysis at the CMS experiment, one that bridges two distinct areas: the search for magnetic monopoles using missing transverse energy, and the precision luminosity monitoring through Z bosons. Both are technically demanding and scientifically relevant topics within the LHC program. And today, with his defense, this all culminates into his doctoral defense, and probably also into a sort of celebration of perseverance and growth for Thales. And with that, I don't know if Albert wants to say something. Otherwise, I will turn over to Thales, who will talk about the search for magnetic monopoles with missing transverse energy and the luminosity monitoring with the Z counting method in the CMS experiment.
I'm good if we go to Thales.
Okay, thank you, Albert. Thank you, everyone, for being here. And Thales, if you want, you can start.
Okay, so thanks for the wording and the presentation. I'll start with the slides. Just give me 1 second to do it. So assuming that everyone can see the slides in the screen, just to confirm it.
Yes, perfect.
Okay, great. So as already presented by Carsten, I'll be presenting the search for magnetic monopoles with missing transverse energy and the luminous monitoring with the Z-boson counting method within the CMS experiment. So I would like to thank my supervisors, as Carsten and Albert, for all the support during this work, and then probably can elaborate on this after the presentation. So presentation is more or less section in different topics, so I'd like to have some words on the theoretical motivations behind the magnetic monopoles. Additionally, we have some ideas on the experimental setup that we have, especially how the luminosity was measured within the CMS. Later on, we discuss about the monitoring method itself with this it's all these technicalities, and then you dive deep on the search for magnetic monopoles, and then you will have some words in the conclusions and probably future work within both topics. So as a starting point, we can start to look at the magnetic monopoles from a classical standpoint, so from the Maxwell equations within the classical electrodynamics. So at first, these equations present some asymmetry between the electric and magnetic fields, in the sense that we cannot observe any kind of isolated magnetic charge or any kind of divergence of the magnetic field, in contrast to what we are seeing with the electric field. So the electric charging currents will be the main generators of the both electric and magnetic fields. However, if you think an introduction of a magnetic charge or some kind of particle with magnetic charge, we can achieve what we call the completion of the electromagnetic duality between electric and magnetic fields, and then we can restore the symmetry of the Maxwell equations, where we will have at the end both electric and magnetic fields being generated by different contributions, by different divergences on the magnetic field and the electric field, for instance. So if we use a different framework, the quantum field theory framework, we have monopoles in granular field theories, where we expect we explore its, let's say, this role in charge quantization, in the charge quantization. So in these models, there are some solutions within some models, especially when you have the electromagnetic group within a non-abelian group. That could be, for instance, SU2 or SU3, which is very similar to the standard model that we have at the moment. And later on, from works with Tihoft and Polyakov, there are in fact some topological solutions, a certain range of models where you find that some components of the electromagnetic field tensor will not be let's say satisfying the Maxwell equation, and this could lead to some magnetic monopole topological solutions. However, this is not necessarily related to magnetic charges, so this is an interesting point, but probably the most interesting work within this topic could be the developments from Dirac. So starting with the idea, it explained as the electric charge quantization as a consequence of the quantization of the angular momentum if you have some kind of magnetically charged particle. So from this work, we developed what we call the Dirac quantization that basically relates both magnetic and electric charges in a constant. And then from this, you can derive some kind of relation between both charges, and then you discuss this with a little bit more details in the future, because it is quite important in this context of especially looking magnetic monopoles in the experimental point of view. So we return to this later on. So with this, the building on top of these previous initial developments, we arrive at the electroweak monopoles, where we have some extra proposals and ideas, but however, with not well-defined mass or masses even reaching the grand unified scale, which is quite interesting, quite peculiar, especially in the context of colliders. However, when with the development of the Shunkin and U model, you have electroweak, the rare monopoles in these electroweak scenarios where the mass could be accessible to the LHC with a field TV. So this becomes this makes this kind of particle to be available in the particle colliders that we have. So building colliders, some searches. There is some small cosmic searches which targets magnetic monopoles in the early universe. So for this kind of searches, it uses a wide range of different techniques, including interferometer, telescopic, different neutrino detectors. I find quite interesting, by the way. But if you are looking in the direct detection of it, the main idea would be exploit its unique signature. It would be composed by anomalous track in the presence of a magnetic field, and also how then the kinetic energy of this particle would be trapped in the material. And this will be directly related to the high ionization capacity that this kind of magnetic monopole particle intrinsically have. And then this will lead to the collider searches, where we are expecting to find these particles in a reproduced fashion from different benchmark production modes that will be discussed later on. However, this study is a little bit trickery, because from the large magnetic coupling constant between photons and monopoles, it will make not possible to use perturbative methods in order to make cross-section predictions. So this will make Feynman diagrams a little bit tricky, but nevertheless, you can use it as also an informative tool. So some words in searches in colliders have electron-positron colliders that has different methods to search for this kind of particles, exploring inducing currents due to the presence of a magnetic charge, and then also for the exploitation of non-helical trajectories. So in the large electron-positron collider, there were some early studies with magnetic monopoles masses around the electromagnetic scale for the significant range of magnetic charge. That was the first set of limits within those particles, and then we arrive at hadron colliders with special attention to Tevatron and Hera. we exploited masses a little bit more with in the center of mass energy, and then we arrive at Moedal, which is a dedicated experiment to search for monopoles, exploiting the fact that the monopoles will be trapped inside the matter. And then we arrive at Atlas. We exploit the high insertion signatures, and for round one, it was able to establish some limits using the Drarian production mode with masses around the TV scale that will be part of this work. So as I already mentioned, magnet monopoles could be produced by what we call benchmark mechanisms, which is basically Drarian and photon fusion that we find in pairs. And we can tune it in order to have masses around some few TVs which will be accessible for LHC. And as already mentioned, from the equivalence between electric and magnetic charge from Dirac, the main energy mechanism laws of this kind of particle will be the ionization process. And when you can start with the standard bat block energy loss equation, but when we make let's say the changes, the implementations for deal with particles with magnetic charge, with also some corrections. In order to do it, we arrive at different bat block equation. But the main result of this is that the fact that exploiting this equivalence of 68 electric charges of a magnetic charge, the energy lost by a magnetic monopole particle or some kind of particle with magnetic charge will be in around 4 orders of magnitude higher than an ordinary particle, and this will make the study of this kind of particles in colliders quite interesting, but a little bit more challenging because it wields a very different signature. But this will be elaborated a little bit further. So the setup that we have, it's the Large Hadron Collider, as we're already very familiar with. So we have the largest and most powerful collider to date. For round 1 and 2, basically collided protons and lead ions, but now for round 3, there were some collisions with oxygen and neon ions. Did not have so much knowledge of it. But LHC is composed by a lot of small experiments, but we are basically most familiar with the 4 largest ones. Would be ALICE for heavy ion collisions, LHCb as a B factor study to study B physics, and also the Atlas and CMS as a multi-purpose or general purpose experiments that we can use to study a wide range of physics phenomena and so on. And within the LHC, we have the compact neon solenoid, or simply CMS, which is designed to provide high precision measurements of particles produced within the LHC. I would like to highlight for this presentation specifically the tracking system, which provides a high spatial resolution, and it's all built with silicon, and especially the electromagnetic calorimeter, which is composed by lead tungstate crystals, and make it the equal from CMS a homogeneous calorimeter, in contrast that we have in Atlas, which is a sampling calorimeter with two different materials, among two different materials filled in the electromagnetic calorimeter. It provides fast response, high granularity, but it comes at a cost of a filtering that was designed to deal with noise suppression, because some functionalities of these crystals and this SFGB algorithm is quite important for this context, and you have a lot to say about it in the future. So to finish, we have the trigger system based on hardware and software by the level 1 and high level trigger, and then the reconstruction where you have a special algorithm in order to provide a global event description and reconstruction within the CMS. So from CMS, we have to start this work discussing about luminosity in the collider context. So in general, start looking at the luminosity by the number of events produced for a given time interval of a given process, which is understood by the cross section to make the probability of this event to occur. So from this, we can build the luminosity as a measurement of the collision rate per unit area. So the higher this collision rate, the best to have a higher number of events. And for across round 1 and round 2, let's say delivered to CMS a wide range of integrated luminosities, where for the current and ongoing round 3, we're expecting around 300 inverse femtobars. And if you take a look, if you take in consideration the high luminosity LHC, which is could be say right around the corner, we'll expect a factor of 10 in this delivered luminosity, and you can also expect an increase in the instantaneous luminosity where we can aim to study more hard process with more statistics in the future. So, but on the other hand, we can obtain this luminosity by machine parameters with after a series of implementations, you find that the proportional foot through an effective collision area, and then we should be able to make an estimative on this collision area by a method that we call the van der Meer, which is basically measure the proton bushes overlap and give us this with it using X and Y in order to make this the estimate on the area, and then we can have estimative on the luminosity. So after the measurement of this luminosity, we can use it to calibrate what we call the visible cross-section, which is basically the absolute scale of a luminosity detector. And CMS is composed by 6 different luminosity detectors, while in Atlas, if I'm correct, they have just one luminosity detector. And this visible cross-section could be understood as a one-time calibration constant for the entire data taking, which is so it's quite interesting quantity to have a good precision, a good estimative on it. So at the CMS, you can employ a two-method approach in order to get the luminosity. So at first, you use the van der Meer method to get the calibration for the absolute luminosity scale. This is performed under a very specific LHC field with special optics with a low level of pileup. So this is quite important. So it's called the van der Meer campaign. And we can use, and this is be used for a lot of different things inside the experiment, especially regarding the luminosity. And then after this rate, we can integrate it over the entire data taking advantage of this visible cross section that you get that we measured and calibrated in the previous steps. However, this integration, it's basically take the measurement from this very specific LHC field with very low pileup, and then we have to integrate in the physics condition where the level of pileup is quite high. So this is a little bit challenging. So in the ideal world, we expect this integration to be quite smoothly, quite seamless, but this is not the case. Have some non-linearity during this integration because the luminosity detectors are in fact most of it dependent of pileup. So this would be a very relevant source of systematic uncertainty for the luminosity measurement. And in order to deal with this uncertainty, we have the Z-counting method and also the usage of low pileup datasets as a method to tackle this challenge. So the Z-counting is basically a method to determine the luminosity from a physical process rather than through machine parameters as we saw previously. And then we specifically use the Z boson decay in 2 muons because it's a very clean final state. We have a very clean signature. We have a very good knowledge of the cross section. And inside CMS, the muons could be reconstructed as with a very good efficiency. And this method is also important because it takes advantage of what we call in situ measurement, where you can use the same set of muons that we have been employing to count the number of Z bosons that you look for, and also you can use the same to also estimate the efficiency. So this makes the method quite robust against, for instance, external calibration or external information, especially if take consideration that you have to have at least one van der Meer per year in order to calibrate. So this is quite in handy. So with this luminosity from the Z bosons, we can use to determine the integrated luminosity and then also provide some relative and absolute measurement, especially in the context of making comparisons between CMS and Atlas in the context of delivered luminosity by the LHC. So in this scenario, we can use the number of Z bosons that we are counting in Atlas and CMS to make a cross-check between the relative luminosity, the relative instantaneous luminosity delivered through both, and then we can reach this kind of plot, which is quite it's quite busy, but it's basically the ratio between the Z bosons delivered or counted within Atlas and CMS for the field for the different months of 2018 data taking. Additionally, if this method we can do what we call the transfer loss luminosity calibration, because we are assuming that we're not changing the energy of center of mass for any year of the data taking. So this will make that the fiduciary cross section is constant, and then we can calibrate the luminosity scale in 1 year and use in the remaining years of the data taking. And then this calibration will be done preferably at a data set with very low pileup, which provides a high precision in the measurement of the reference luminosity, which leads to the higher precision in the visible cross section. And then with the visible cross section and the Z counting, you will be able to minimize the integration uncertainty that we are basically trying to tackle with this. So the low pileup data set, just some context in 17, in run through it was taken in 17, what was collected around 200 inverse picobars of data with an average level of pileup around 3. And for run 3, I was the representative of the CMS Z counting team in order to propose to take to the LAC this request of a dedicated low pileup data set for run 3. And then it's probably we took around 2026, where we expect to collect a little bit more data than it was for run 2, but at the cost of a little bit more level of pileup. So from the method, we can estimate the efficiency from the tag and probe method, where we are basically selecting muons with a positive electric charge under a certain invariant mass window. And then with the building of these distributions for the scenario where we have one event within the high-level children, or the scenario we have 2 events, we are able to have a fit on those 2 distributions, and then we are able to extract either both the number of reconstructed Z bosons that we're using to estimate the luminosity, and also the efficiencies of, for instance, of the HLT. So this builds on the idea that we can extract both quantities using the same data set. And the result that we achieve is the one that we're seeing on the left side. So this is a typical HC field in terms of the instantaneous luminosity as a function of the runtime of the field itself. In red, you have the reference luminosity, which is provided by a conventional luminosity detectors or a combination of those detectors. And in black, you have this measured Z boson rate, which is basically the Z boson that obtained directly from the Z boson method, this boson counting method. Have some input on the reference as well. But we can see that we have a very good agreement between the 2 almost independent measurements, especially for the end part of the field. And these results could be obtained in a field basis. So we can have one of this plot for each LHC field for each year of the data taking. So we can have a very good collection of the plots that we are seeing on the left. And on the right side, you have basically the efficiencies, the single mirror efficiencies that we're using in the method. So I would like to highlight the overall very efficient reconstruction of the muons by the three distributions I see in the top, with a special attention to the high-level trigger, which has a little bit less efficiency, and as you can see, depends slightly on the runtime, which is to mean that they are also dependent slightly on the pileup, and this could be some other challenge to tackle in the future, especially for the high luminosity LHC. So just some words on linearity. So the idea is to observe how the fiduciary cross section of the Z production will behave as a function of instantaneous luminosity in order to study possible deviations that was probably originated in how we are determining or how we counting the Z bosons within the fields. And you can see that it's overall linear with this idea. So this fiduciary is quite well behaved, but to have some attentions to the lower values of instantaneous luminosity where you have some let's say higher errors. And we reach probably the most interesting and relevant result of this, which is basically the ratio between the luminosity from the Z method and also the reference luminosity. So each entry that we are seeing, it's basically comprising 20 minutes of data for the 2024 data set. On the left side, we have the results for what we call the offline. On the right side, what we call the online. So just for extra information, the offline is basically the higher data integrity that we can achieve, where we have the application of the data quality monitoring for the fully operational CMS, and it's basically the data that we use for physics analysis. And on the right side, we have what we call the detector control system, which relies on a stable CMS operation, but with no data quality monitoring. But on the other hand, could provide to us a broader coverage of data with more luminosity and also quicker in terms of how long it takes to be produced. So another way to look on this ratio from the last slide is study its behavior as a function of integrated luminosity of the data taking. So this would be exactly this plot. So each point represents one Z-rate measurement, where each size is proportional to the luminosity that were collected. And this is the plot for the offline data, where you can have similar results for the online data. I would like to highlight for this scenario that especially that the online data, it's quite interesting as a tool for performance and calibration, because we can in general spot quite clearly different VDM campaigns, the different calibrations, changes in detector. So this plot is quite important, especially if you take this, especially but complementarily if you take this exact same plot but as a function of LHC field directly. So if you have different calibration, have some VDM campaign between given two fields, you can export directly with this kind of plot by the study of the rate of the Z bosons. So as a quick outlook, so the Z boson production is a very interesting tool for luminosity monitoring, where you can provide cross-check between different CMS detectors, because it has what we call a long-term stability and what the self-calibrating nature, which is basically the idea that you can determine the visible cross-section at the dedicated data set with low pileup and use it for the whole data taking, instead of relying in an annual Van der Meer calibration, for instance, which is the case for the standard luminosity measurement. So this makes the method very robust for long periods of data taking, for instance, like the one that we have now. Splitting on this transverse luminosity calibration, and they probably have its best use in the reduction of integration uncertainties. That is one of the main uncertainties on the luminosity measurement other methods. And then some smaller and systematic uncertainties. They were basically focused on what we call the transverse factor, just basically the ratio between the number of Z's that we are collecting in physics conditions, or a regular LHC field, and the number of Z's that we are collecting in a dedicated data set with low pileup, for instance. So other sources that you can look for is the HLT, because in events with multiple muons, this correlation factor becomes a little bit more needs a little bit more attention, especially with the increase of pileup that you're expecting for the high luminosity LHC. There is the resolution of the outer track, which is quite low in comparison with the inner track, and this could lead to some actual uncertainties, a topic of discussion, and also we can improve the signal modeling as well. So this finished the part of this accounting, just 25 minutes. So now we can dive deep in the magnetic monopoles work. So we have the Monte Carlo samples used in this work as a spin zero and spin half non-relativistic monopoles, which is beta independent, that were produced using MedGraph. But it's both benchmark production modes, that's already mentioned, like Teoria and photon fusion, and we use the Gen4 to simulate this interaction with the detector. So the data we are using is the official production for the run through, where we have the mass points ranging from 1 to 4.5 TeVs, and the magnetic charge that we're considering is just one magnetic charge, which is basically the Dirac monopole. So some small remarks: the higher cross-section for photon fusion production modes, which was implemented and suggested and implemented as a way to increase the sensitivity of the analysis, because late in previous works we had only the Orion production modes. So this is also a part of the improve. On the right side, you can see just a small comparison of the transverse energy, generated transverse energy for different monopoles, and you can see that they are quite interesting, not that small. So how can we search this kind of particles inside the CMS? So the monopole candidates are quite unique because we expect some kind of acceleration because of the magnetic field, which is very uncommon for even exotic particles. And we can identify these candidates by using two discriminant variables, which exploits the large number of saturated tracks produced during the passage of a magnetic monopole through the tracking system, which will make it, and then also can exploit its narrow and concentrated energy deposits within the Ical crystals. And this was basically built on the on the fact that the monopoles lose its energy very quickly in comparison with other particles. So, however, how all this peculiarity from the monopoles, it's this magnetic charge which interacts with the magnetic field, which is not that very common, and also this ionization capacity comparison with a ordinary track, a normal particle, it's also quite unique. But on the other hand, this will make the standard reconstruction algorithm from CMS quite inefficient. So in order to tackle this, a dedicated tracking algorithm was to be developed to deal with the monopole tracks. So it's basically the composition of different standard track segments in order to build what we call a curved track or just the monopole track. And on top of this track, we apply two different fits. The first one is a circle on the perpendicular plane that we can extract two parameters like the impact parameter and also the radius of this fit. And later on, we can apply also a parabolic fit in order to account for this the expected curvature. And we can extract three extra parameters. And when we compose these 5 different fit parameters, we can have what we call our pre-selection set of cuts or just quality cuts that is related directly to the tracking quantities that we are observing. And this will make part of the cut flow that we have for the analysis. But now we arrive at the SFGVB algorithm, which is basically a spike filtering algorithm. This will be in the idea of the equal spikes, which is basically anomalous energy deposits in one isolated crystal, which can mainly be related to noise or some malfunction of the crystals. This would make inconsistent shower shape, so this would be interesting to be not present in the reconstruction. So this is where this strip finite grain Vito-bit algorithm comes in handy, where this is built in both level 1 and high level trigger in order to prevent this kind of spikes from make a large missing energy in the reconstruction. And the algorithm is quite efficient in doing this. But on the other hand, due to the nature of our magnetic monopole particles, this is basically what our signals look like. So in other words, we can say that our signal is constantly being rejected by both level 1 and high level trigger, and this results in a remarkable loss of signal efficiency. And then this will lead to development of different analysis strategy in order to tackle this limitation, and those analyses will be discussed in the next slides. So building on the identification of the monopole, if we exploit its ionization capacity to produce a high ionizing signature, we can combine the total number of strips that we have for the given passage of a monopole and also the factor that was saturated by this passage. And then we can use these two quantities, the total number and also the fraction of saturation, to produce a probability, a binomial probability, where you can start from this plot on the left side, where you can see quite clearly the difference of, let's say, the regular data, the regular and the minimization particle, and also the monopoles. And building on this probability, you can build some kind of variable that you can use for discrimination between background and signal. And you can see quite clearly some inflection point around 5, right? It's quite different between the signal and the possible background. And then for this reason, we use the signal region cut around 9 for 2018, for instance. For 16, it's a little bit lower. But this is our first discriminant variable on the analysis. And the second one is the fifth one. So from its high energy loss pattern, we expect some narrow and concentrated deposition of its kinetic energy, even in single crystal, which is problematic because this will trigger the application of the spike filtering, and you don't have any events at all. So then we will be relying on the deposition in more than one crystal, where we can explore its possible deposition along eta because of the field. And in this scenario, we will avoid the spike filter and have some inefficiency to work on. So exploiting this deposition pattern, you can build a topological cluster variable called F51, which is basically relating the energy sun in this particular 5x1 strip in eta, and also the energy sun in a regular 5x5 square of crystals. So this will lead to magnetic monopole particles with values of F51 quite high, ideally close to 1. Because most of energies will be deposited basically through crystals, basically in one, but will be rejected. So this is a different story. But a limitation from this is that F51 is only applicable in the barrel. So this will make this analysis only available in the barrel, and you can tune the signal region for the monopoles to be F51 higher than 0.85, for instance. Now that you make sure that you can use this F51 variable in this work, you have to exploit the shower shape modeling of this variable in Monte Carlo, special attention with the F51 and the 5x5, which is energy in the 5x5 square of crystals. And then we use what we call the equal reconstructed hits, which is basically assessing crystal level energy deposits within the equal as an input for the clustering or object reconstruction methods. So this study you use this study produced a hyperwidth sample within the Darwinian Monte Carlo in order to have a ZDK in natural electrons, and then we use data from E gamma under the control region that we have defined on the left side, and then this will lead to this kind of comparisons where we can see quite clearly a good agreement between data and Monte Carlo, and this will lead to the validation of the F51 variable, and then in consequence its usage in our analysis. And additionally to these studies that can be done using the equal reconstructed hits related to the monopole, we from the generation level Monte Carlo, from the generation of slow moving monopoles, we'll be expecting some kind of delay in the arrival time of these monopoles, for instance at the equal, in order of a few nanoseconds. This will be dependent of the mass, so the higher the mass, the higher the delay. This at first hand could be interesting because we can use this delay as a possible trigger to long-lived signals within equal. But on the other hand, this comes with a cost of bias in the reconstruction, because from the equal pulse reconstruction, where you take the reconstruction amplitude of a given equal pulse and also divide it by the true amplitude of the signal, you can see some kind of bias, some kind of linear correlation, where we basically are overestimating by 1% this amplitude as soon as we get 1% of delay. So this will lead to some kind of bias when you have the clustering of the monopoles, the energy deposition of the monopoles because of this delay. So the way that we approach this was to exploit these timing characteristics using the Heck hits, where we expect some kind of distinction, spatially and temporally from regular particles. So from our Monte Carlo available, especially Drawian spin-half, which is basically also present in the private production, we select some associated Heckates to these magnet monopoles with a significant amount of energy, and then we produce the results that we see on the right side. So on the top part we have the energy on the y-axis and the time on the x-axis for hits associated to monopoles with 2.5 thousand GeVs of mass, and you can see quite clearly there is some kind of accumulation, a higher density of occurrences around 5 nanoseconds. And this will also happen for the 4.5 GeVs of mass, but now around 8 to 10%, 8 to 10 nanoseconds. And this result is in coherence of what we're expecting from the generation that we have, where we have some delay, and this will lead to the motivation of time-related corrections that could be developing, that could be taking more details later in the analysis and possible in future works. So now we can came to the final strategies to search for these monopoles. So the first one is what we call the photon analysis strategy, which basically takes the magnetic monopole in the role of a fake photon that can fire the single photon trigger. Just basically means that you have energy deposition pattern that is spreading for more than one crystal, and then you can avoid the spike filtering. And on top of this spike filter, you can also incorporate what we call unclear clusters collections, which is basically clusters that have this spike filtering bypassed. And then to lead to the center of this strategy, which is basically the usage of a single photon trigger, which is around 175 and 200 for 16 and 16, and then 17 and 18. And this is basically the shape of this strategy. We have the single photon trigger applied, have a candidate energy requirement that follows the threshold of the trigger path for the first 16 and 17 and 18, because the trigger has to be changed due to pre-scale problems. And then we can also apply the two significant variable clusters that we're having in significance and also F51. And this is the first strategy. The second one is what we call the PF match strategy, which is basically complementing the first one in the scenario that if you have, let's say, a regular magnetic monopole energy deposition pattern, which will be then rejected by the spike filtering because it is very similar to Equal spike, this will lead to some kind of missing transverse energy in the event because this energy will be not there. So we can trigger on this absence of energy in the case of presence of missing AT. And this leads to the first evaluation of two different strategies, looking for the calorimeter towers and also or the particle flow algorithm, where the second was selected in order because it has higher efficiency, as you can see by the right side. And you can see already that this PF match triggers, this match trigger related, could reach around 30% of efficiency, which is not very much, but you can see that it can become even smaller than this, but this will be in a moment. So we have also studied performance in Monte Carlo to make sure that we can use this PF match triggers in order to capture events from magnetic monopoles. And then will be the face of the strategy. So we apply a combination of the match trigger, the PF match trigger, and the single photon because we have to take in consideration the events that can fire both triggers, which is basically the overlap region. So in this overlap region, we made a study in order to see what strategy we deliver the higher efficiency, and this result belonged to the photon strategy. So these events in the overlap region were treated by the photon strategy, and in this PF match strategy, we're basically dealing with events that fires the match triggers but are not firing the single photon triggers. So in this, we avoid any kind of double counting. And then in this analysis, we will basically switch the energy requirement in the candidate to apply some PF match threshold in the event. And those thresholds are quite higher because we are following the efficiency, the PF match efficiency curve, trigger efficiency curve, which has a plateau around this value. And again, the significant variables are the same. And then we can lead to the signal efficiency. So we are evaluating how many events survives the cut flow directly. So the high level trigger, the tracking, the 5x5, FF, and the two significant variables. And you can see on the left side, the overall signal efficiency for the particle flow match trigger. And you can see that is quite low, especially for photon fusion processes in red and blue. But we have some efficiency around 8 to 10 to 12% for Darwinian methods. And you can see for Darwinian production modes, and you can see quite clearly that these signal efficiencies are not very significant. But if you compare with the overall photon strategy, even that we have a more, let's say, stable, consistent efficiency for the different mass points, you can see quite clearly that the values are way below, because we have around 2 to 3% overall signal efficiency for all the mass points for 3 different production modes, with a special attention for the signal efficient peak around 5% for the variant spin 0. So you can see quite clearly that the efficiency that we have, the number of events that we have available are quite reduced, and this is most related to the impact that the spike filtering algorithm have in the magnetic monopole signals. So one question that you might ask is, how can we assess, how can we evaluate this impact? So the idea is replicate the study, but now not considering the high level trigger, or considering that it has 100% efficiency. And you can see just by the start of the plot that is provides a very high efficiency, which is around 30% for the production modes, except in the zero variant spine 0, which can reach almost 60% of signal efficiency. So we can see quite clearly the impact of that the high level trigger has in the analysis, because in the scenario that you have a dedicated high level trigger with a 100% efficiency, not very feasible, to be honest, but it could be something closer to this. You'll see that this efficiency that you have available in the analysis will be quite higher. So with this result in hand, compared with the result of the previous slide, with, let's say, the standard analysis workflow, you can have an estimate on how many events are being treated as radical spikes and later on rejected by the spike filtering. And you can see quite consistently that 90% of the events are being treated as a nickel spike. So for each 10 events that could be used for the analysis, 9 of them are being rejected by the spike filtering. So this also highlights the remarkable impact that this filtering has in the analysis, and also the absence of dedicated high-level trigger. And then we can also evaluate the efficiency of the analysis in overall, so by the relative efficiency, so you can access the efficiency for each one of the cuts that we have in the analysis. So I brought you 2 different tables, one belonging to the photon strategy and the second one belonging to the PFMAT strategy. You can already see by the trigger line that the trigger efficiency is quite low, especially for the photon strategy, which barely reached 7%. But with the application of the PFMAT trigger, this efficiency improves by a factor of 3, even higher for certain mass points. But overall, the analysis is quite efficient. So we have, for instance, for the photon strategy, basically the efficiency higher than 90%, excepting for the fifth one. And for the PFMAT strategy, a similar efficiency could be observed, but the application of MAT threshold, especially this high PFMAT threshold, which is way higher than, for instance, the requirement that we're applying on the energy, this also plays a significant role in reducing the signal efficiency. So we gain some efficiency from the trigger, but we lose some of this efficiency by the application of the PFMAT trigger. And this will happen because the high PFMAT threshold that we have, which is done based on the trigger efficiency curve that we developed. That can also be found in the slides. So, I mean, this is kind of a peculiar analysis with a very peculiar kind of particle. So there will be no surprise to no one that we do not have any kind of expected Monte Carlo background to this analysis. So I have to rely in a data-driven method, which is the double ABCD method for background estimation. And in this framework, we start with 2 uncorrelated variables, which is the 2 significant variables that we derived for this analysis. And then you can build 5 background dominated regions, 1, 2, 3, 4, and 7, and then 3 control regions, 5, 6, and 8, for different values of F51 and the IDS significance. And then we can, from these background dominated regions, obtain expected background in the control regions by the equations you see on the left side. And then with these results in hand, you can we can start to thinking on the unblinding of the signal region. So for this, we have the study using the full run-through datasets for both E-gamma datasets from the photon strategy and the missing ET datasets for the missing ET strategy. And starting with these control regions blinded at first, with a good agreement between the expected values and the observed values. When we unblind the control regions, we should be able to unblind the signal region and then have an estimative on this value by the left side that we are seeing in yellow. So how this look like in our data? So on the left side, you have the result for the photon strategy, which uses the E-gamma datasets. We're expecting around 2 background events on the signal region. And on the right side, you have the same result for the PFMAT strategy, which uses the missing ET dataset, where you have 5 expected events. But these results should take in consideration with some extra information, because the result on the PFMAT could be affected by spikes contributions, because basically when you have a trigger like the E-gamma trigger or the single photon trigger, we at least request that is one object available. So the initial spike is not the physics objects, and then this will not basically not passing this single photon trigger already. But the PFMAT strategy, since MAT could come from anything, a lot of things, a lot of different sources, these requirements not present in the PFMAT. So this could lead to some, let's say, not physics events, especially in the third region of this ABCD scheme. There is some study done in the thesis, some study done in the backup. So these results should be taken with a little bit more consideration than the one from the photon strategy. So some words on the systematic uncertainties. So starting from its high ionization signature, which produce a lot of secondary electrons around the trajectory within, especially the tracking system. This lead to the delta ray production that we know, which is the dominant source of the systematic uncertainty in the analysis, at least in the Monte Carlo level. And then you can have an estimate on this, but basically calculating the signal efficiency with the delta ray and without the delta ray effect on the Monte Carlo. And you can derive the table that we're seeing on the right side. And this efficiency fluctuates quite a lot. We have also a systematic uncertainty related to the crosstalk within the tracking system, which is not that much contribution. We have an estimative on the data-driven background method, which is basically we're taking 100% uncertainty because some results from 2016 missing ET datasets that are present in the backup. We take an estimative conservative estimate. We have the uncertainties related to the missing AT usage, because we have now to take in consideration the jet energy calibration, since the jets are the input of the missing AT. We'll have some extra contribution, and also taking consideration the luminosity uncertainties from the LUMPOG, which are displayed here. And then we reach at the final result. So with all this information in hand, we can derive some 95% confidence level limits on the production cross-section for the combination of both strategies that we develop for each one of the production modes. So one plot for each production mode, where you would like to highlight later on a little bit on the photon fusion higher sensitivity because of the higher theoretical cross-section. So the results that you're seeing on the left side, which is for the Ariane spin half on the top left, the Ariane spin 0 on the top right, and spin half photon fusion on the bottom left and bottom right, with photon fusion for the spin 0 data in the Monte Carlo in this case. So the higher the cross-section, the higher is the sensitivity, and those results were produced by the combined tool from CMS, which is basically assuming that we have a counting experiment, and this was used for blinding data, so it's an expected limit, not the observed limit, and then we have some cross-section fixed for this kind of calculation. So if you make the intersection between our experimental limits and the theoretical prediction, you can see we can derive max exclusion limits from this intersection, which basically you can see quite clearly the higher exclusion limit for the photon fusion. And these results are the stringent CMS lists developed to this date, especially compared that we have now 3 extra production modes that we have in the past. Results are quite interesting in the scenario that most of it was, let's say, unprobed to this day. So just to finish up, which is around more than 50 minutes. So I have Z counting as a method with linearity and long-term stability for run 2, run 3. And be used for further data taking. So we have establishments for the future to try to get the independent luminosity measurement for this method itself, and then use it heavily to improve pileup dependent uncertainties heading to the high luminosity LHC, which we expect a very significant increase in the pileup level. So this method could have even more relevance. And then we have for the search for magnetic monopoles, we probed magnetic charges through one direct magnetic charge for the first and two data sets with two different strategies. One employing PF Mason related information in the workflow, which produces an increase in the overall sensitivity of the analysis, produced the stringent CMS limits to date, and also produced new limits for production modes that were not probed in the past. And from the max exclusion, we can also make a comparison with Atlas. So based on the significance that we have that is affected by this, the CMS equal, we have a competitive results with Atlas. Remembering that Atlas do not have any kind of spike filtering built in its trigger, and also have a dedicated high-level trigger path. And as a future development, we consider to produce some kind of, to develop some kind of dedicated high-level path to exploit this increase in staggering efficiency. We can exploit, for instance, AXO level 1 TL or also cicada strategies in order to develop this kind of new trigger for high ionization particles in general, and also the magnetic monopoles. So this is the presentation. Thank you for time. Thank you for attention. Thank you for the patience for the 3 extra minutes. And that's it. Thank you.
Thank you very much, Thales. That was a very nice presentation. If there's nothing else, I would say we go to the second part of the defense, which will be the bunker asking questions. So I think we should start with our referees from Sao Paulo. Marco, why don't you start?
Okay, can you hear me?
Loud and clear,
Yes.
perfect.
Okay, let me turn on my video as well. It's just now I think you can see me.
Yes.
So thank you, Karsten. Thank you, Albert. Thank you, Thales, for the invitation for being present on the evaluation of this nice work. I am very pleased to see the results. I think these are very important and significant results, even more on the brink of the high luminosity. So I will try to go more quickly on the points that I think that are that I'd like to have a few more input, and I will leave some comments that I had, a few details on your writings that I can send to you later for fixing. I starting on your, let me grab my notes here. Okay, starting on your luminosity, you I think you mentioned at some point that Atlas only has one luminosity method. Actually, because I'm of Atlas, of course, I have to bring this on, that the Atlas actually uses the four detectors for this. So, of course, there's the main luminosity detector, but we actually use the information from the tracker and the calorimeter and a dedicated beam condition monitor. So maybe I can start with a question here. What's the main limitation on CMS on not using the electron channel on the ZE count on the Z counting for the luminosity measurement?
So currently for CMS, we have only the mid decay in 2 millions that we have seen. So there were some proposals in order to also include the electrons in this study, but for the moment, those was more in the field of ideas and implementations rather than to in fact being developing. So the idea of the method is to get to be used as a way to get a different approach to deal with the integration uncertainty, which is one of the main sources of systematic uncertainties within the luminosity measurement. So I would say probably that if probably lacks of person power, so we have more people really associated to this. Probably one of them will be let's say assigned to this kind of limitation, which is also something that was already requested to implement that CMS. So for now, these are the things out. I can say there is some idea to have this implemented at CMS because Atlas have it, so this will increase the comparison power between both experiments. But for the moment, the focus is in improve the method, change it a little bit how the data is being processed, because with the current status, we have some, not say problems, but some limitations for the systematic uncertainty derivation for the method. So the focus for now is to improve this as much as possible to be using for this, probably this run tree data taking, and then I think later they will be dedicated the efforts to this implementation of the electrons in the Z counting, let's say, proposal. But they are quite relevant because the Atlas have it, so CMS also have it in its pipeline. So this is quite probably the enough reason to do it. So
I see. And I see that you mentioned several times in your writings that this becomes a kind of cross calibration with the van der Meer reference. You don't have we cannot have van der Meer to every as much as we'd like to have, but do you have an idea of which analysis would be more impacted by the improvement on the luminosity determination, using the Z counting instead of just relying on the standard van der Meer numbers that we have?
okay, so probably one of the main associated analysis would be analysis related to top quarks, because the luminosity measurement uncertainty is one of the main sources of systematic uncertainty. So just a quick example, when we produced the detector performance summary for the Z counting, basically like in the next week there was some citation to it from the top analysis, because this uncertainty of the luminosity is quite relevant in this context. So the better you can do this measurement, the better you can reduce this uncertainty. This is probably one of the analyses that will profit the most from it. And also, the Z count will be, I mean, the ideal world probably not happening, not in the early future, but in the ideal world, as soon as we have one very good derivation of the calibration constant for the luminosity, we don't need any kind of intermediate anymore. So this is, let's say, the utopic objective of the method. So if you have a good estimative, you cannot need to rely on van der Meer again, because you have the value and that's it. Because do not expect to change, because the Z physics will not change in the data taking, basically because the center of mass. So if you increase the center of mass, this will need to be addressed later, but this is another topic.
Okay, I wouldn't be so emphatic on dropping the van der Meers
Yeah.
across the things, because we haven't seen many non-linearities that are coming. Well, on the van der Meer also, but it's a long story. But I mean, I think that it's nice really to have another handle on the luminosity as we go to even higher pi laps. But I wouldn't say that we wouldn't need to have more Vandermeers. I think it's going to be the standard tool for quite some time. I have to browse here. I try to be yeah, on your page 89, when you mentioned the signal modeling.
You mean the thesis?
On your thesis, yes, page
Yeah.
89, right? On line 3626, you mentioned that there's no significant dependency on the number of primary vertex that was observed. Can you probably detail a bit more? Because in Atlas, I remember that we have this dependency on the number of mean collisions and the number of primary vertex that are reconstructed. And we have this non-linearity as you have more as me goes up. So there is a sort of an effect there. I was wondering if this would affect your accounting as well. Because after all, you're going to have to rely on the tracking reconstruction, right?
Yeah, so see on the thesis. So this was basically done for results for run 2. So results for run 3 are lacking to this moment, especially in this context that there is some added let's say focus. So from this, for the way that is phrased, that it sees that so there is not any dependence on the primary vertex. So this is probably not entirely true. In fact, there is some dependence because it's also quite expecting then this to play a huge role in the high luminosity LHC, even that the counting could help a little bit in order to deal with this, but to have expect some dependence of the primary vertex, but probably not that much that in this scenario we can use the same template that we have been used, the same signal template that we derived, which is basically DrawEn, that they can apply this template for the whole data taking, so we do not need to change it for different years because we have, for instance, different levels of pileup. So I think the idea of this modeling is more in this scenario. So probably if you're changing for instance the high luminosity, there will be new consideration of this signal modeling. And also for this moment, there is some extra studies that need to be done in the signal modeling because it's also one of the sources of systematic uncertainty in this Z-counting measurement, which is basically a second analysis in this scenario. So that is some dependency, but not that relevant, at least not for different years of the data taking. But this could be.
Yeah, maybe you could rephrase that to
it works.
yeah.
Check. Just note it here.
Okay, this is a simple question. If you go to page 91, where you show your fits to the resonance, it's I think that when you tell the fit is your CMS shape function that you are fitting, right?
So the CMS function, the CMS shape is just before answering this, I changed this the screen sharing to the thesis itself. I believe is okay. Okay, good. So the CMS shape is related to the background, which is basically a flat spectrum. So this is quite a let's say, easiest background to model, and then we can also remove it quite efficiently. So the same S shape and is part of the background, and therefore the signal have some convolution using Gaussians and so on, in crystal ball also, and you have also the fit combining both signal and background. So this
Okay.
the fit in red from this scenario.
Yeah. So if I'm not mistaken, I think you don't mention anywhere the function that you were fitting. I may have missed it, but it wasn't really clear. So maybe you want to include a paragraph or so on the function that you are fitting to the data. Yeah.
Okay.
Yeah.
Okay. I have a check on this. So exactly the same as shape is defined. Yeah, so it's basically convolution between a Gaussian and a Monte Carlo template shape that we developed. So, but this could be probably make more clear. So this would be the function. May it needed a little bit more elaboration on it. Okay. So note that.
Yeah. So page 99, I think this is okay. It's just a remark that I can send you on the
Yes, so page
but
9.
since you are there, probably you have to double check the figure captions. I mean, sometimes they refer, for example, to the like you mean the upper plots here, you mean the main plot and not the pool plots, but I mean just double check the caption. Sometimes I think you mentioned the reader has the impression that there are more plots there, and I think it's not the case. So maybe we can jump to a more interesting discussion, which is on page 104. Yeah. So we can see a trend between this relative luminosity as we go up with so the X label is instantaneous luminosity, right?
Yes.
Okay. So do you have an idea why this trend appears? Because looks like that it's really a trend. If I take the bands on your feet as the fluctuation on the feet that you have, since that if you are going higher, then seems you have a bias towards this. It may be, I mean, beyond the scope of this work to go so much detail, but it's something that will catch people's attention, I think, when you look at this.
Yeah, so this plot is quite interesting. I brought it most likely because it's also a plot that we use it to validate the method, as we did the detector node inside CMS. So this plot needs a little bit more effort because we have to also deliver it, develop this for different years after data taking. So this plot is quite interesting. But the idea is that we have also some kind of trend towards higher values of instantaneous luminosity. But this plot becomes even more interesting where in the scenario that you have, for instance, a low pileup data set where we quite clearly see that you have a point around low values of instantaneous luminosity with very low error bars, and then is a good check of how this dedicated data set to measure this Z boson is quite relevant for the analysis. So this plot is quite interesting, but they will be even more interesting in a few with more effort dedicated to it, especially with, for instance, extra data compared between different years for 22, 23, 24, 25. So this plot will become way more interesting in this scenario. So this is just to give you an idea of the linearity of the method for the certain amount of data of 2022. But this will need extra information and extra comparisons to make the point more clear.
Okay. Maybe okay, maybe we can jump to your monopole search.
Mhm.
Yeah, the main probably I can start with more general questions that I have, and then we can go into details. I mean, one thing that is still unclear to me is how you can really separate your this spikes, which is in Atlas we call the noise bursts on the calorimeter from the real, I mean, from your expected signature. Is just the shower shape on that, or it's an
I don't think I got it completely.
okay.
So
You
how
said that your spikes can really mimic the the signature of a
yes.
monopole in the calorimeter, right?
Yes, yes.
How much confidence you have in saying that these are because I have no idea how the monopole would behave in your calorimeter there, but how much confidence you have or how much contamination in you have on your separation of spikes and real expected monopole signatures. I mean, this is I think that if you understand, your spikes are signaled by the trigger itself, right? So you lose these events. I mean,
Yes.
sense, right? Unless I think there's a condition that you mentioned in your thesis where the spikes, even if there's a spike, it still passes the selection. I don't remember well what was the condition, but I mean, let's assume that you lose that. How can you model this and compare with the shower if this was I mean, if you lose these things on on the data itself?
Okay, so when you have the monopole signal itself, if it is very similar to a spike, that should get basically rejected, and that there is not so much that can be done on top of it. So we do not reach the point that you have on one side events that we believe to be spikes, and on the other side, we have events that we believe to be monopoles, and we can work with these two data sets in order to have a separation between them. So this scenario doesn't happen because the events that are treated as spikes do not even reach this point of the analysis. So they are basically lost. So things that we can do to work on around it is, first one is including what we call the unclean cluster collections in the reconstruction, which means that basically if you have the clean cluster collection, it's just a regular cluster that passes, for instance, the spike filtering criteria. So they are basically okay, good. Not much to elaborate on it. But then the unclean clusters would be the cluster that didn't pass this spike rejection filtering. So in this scenario, we should be able to access at least the clustering, the energy, that the events that were considered as a spike and then are ejected. So we are be able to use this kind of energy information in the reconstruction, but the events are lost anyway. So there is no way to get around these events if they are rejected by the trigger. So one possible scenario is if the monopole hits the crystal right on the boundary and spreads for more than one crystal, this could lead to the avoidance of the spike filtering. So we have these events back in the analysis, so do not believe very likely that have spikes into adjacent crystals. So
Yeah,
in this,
that would reduce your data set quite a lot, right? If you impose
yes, so
this.
these are a huge impact because basically 90% is lost and there is no way to retrieve it. So the approach that you can use it is, let's say, take this as the way to trigger it. So if you're losing the event, the only way that you can, at least one of the ways that you can find it is there are some energy that are not part of the final event, so this energy should be somewhere. So this would be in the form of missing ET. So then you can trigger these events by triggering the absence of energy of these events. So you're triggering by the missing ET. So in this scenario, we expect, we have this 500 GeV magnetic monopole. They are rejected by the trigger, so we should have around 500 GeV of energy less the event. So these will be forming missing ET. So we can trigger this 500 missing ET and let's say bring this event back to the analysis. So this is probably the best way to do it and the focus of this implementation. So this will be the main strategy to deal with this. But taking the events that have been already rejected and use it again, this is quite not very trivial to think of it.
Yeah, because this is part of, if I may, in Atlas, I think this is that these noise bursts, they are a veto on the data quality level. So we can, if we have access to the pre-reconstruction, or we can, I mean, at the AOD level, this can be selected, but in your case, really, it's an issue, right?
There is a way to think around it, but probably something that could be performed in the future if needed, is this spike filtering is only present in the barrel. So in the end caps, there is no spike filtering, or at least not stringent that it is in the barrel. So it would be interesting to exploit the analysis directly in the end caps. However, the drawback would be that, for instance, F51 would be not applicable, so we have to have a different topological variable there. But these will be a very efficient way to avoid the spike filtering because they will not apply in the end cap. So this is a way to go around this analysis. But the second drawback is that if you take the production modes directly, most of the monopoles are produced centrally, so most of them will be in the barrel by definition, by construction. So this is a second drawback in this idea, but it's a way to look at if you avoid that spike filtering, this not be an issue anymore. So you can develop a different kind of analysis.
Yeah, and since you mentioned that, I think one of the things that I missed, that may be my fault because I didn't pay enough attention, was a kind of the kinematic plots for the monopole distribution. I think you have a large number of plots on your discriminants, but I mean, what's the rapidity, the distribution, the PT, the distribution as a function of the mass and so on. I think this you may have, but would be nice probably to add these things, and for the reader would help a bit on spotting these things, like you said, having a more let's say it could be a truth level. We don't even have to do it at the reconstruction level. It's just you have a general image of the how these events are distributed.
Okay, I may have something on the appendix. I brought it some generated level information. So if I can just change the screen. Okay, so this would be generated level, for instance, spin zero photon fusion. And this will be basically how they will be produced within
Okay.
identifying fashion. So that's basically most of them essentially.
Yeah. Well, I don't know. You may consider having it on the main text when you discuss about the production. It's your work. I don't want to get too much into it, but it's
in the main text I plotted for the one of the production modes and the other two are the appendix, because I think it's no needed to have 4 different set of plots for basically the same just to say the same message. So I brought it for one of the production modes in the main text, have eta phi and also the transverse energy.
okay. Yeah, I think that's enough. Jumping now to your tracking selection. For example, on page 126 on your work, I think if you can, maybe we wait for you to bring up this page. It's 126. Yeah. There's a lot of geometrical discussion that is put verbally. I think for the reader would be helpful if you could add a few figures explaining and illustrating the issues there. For the people who are used to the tracking and so on, it may be like more it may be easier to understand the drawbacks. But for a student, for example, that is browsing your thesis, and it may become a very nice reference work, it would help to have these figures to aid the reader on understanding the problem on the tracking. And actually this spun off an interesting question, which you don't have to answer now, but we are both Atlas and CMS are going through remodeling of the tracking system, right? And that also includes the algorithms and so on. Is CMS for because to do what you are doing here to reconstruct the monopoles, you really have to get into the basic parts of the tracking system and basically redo your tracking, right? In order not to have you have to go back to the hits, basically, if I understand. And this, I mean, at least in Atlas, is not something that we have promptly at the high level of the analysis. You have to go back to the EOD and extract all this information, which is quite, I mean, it's a very non-standard, and those, I don't know in Atlas if this is being considered, but do you know if CMS, for example, is considering when puts the new reconstruction algorithm to take into consideration that you're gonna have this sort of signature, so you may have to leave in the reconstruction some room for the user to go back and do this sort of analysis, and not just throwing up these things that are bending on the RZ plane as just a misreconstruction.
Yeah, so for this analysis, we also had to rely on lower level information for the tracking. So I had to use, for instance, AUD in the analysis, which is not the standard procedure. So this add a little bit more of effort in the analysis. But if I remember correctly, maybe Carson have extra information from one of the previous analysis that I was part of with I think one of the students, they also needed to have extra collection information for the dark matter search, if I remember correctly. So there is a way to assess this at the AUD level, so a lower level information. But concerning the CMS point of it, I do not have a clear answer to this. Something that I didn't investigate it that much, but I believe that will be part of it because the main idea is to search for new physics. So new physics could be present itself in the different scenarios, even considering, for instance, particles with significant amount of ionization capacity. But from a particle with this capacity in the magnet monopole scenario, that it could be a little bit different. There could be some limitations on the system, on the tracking hardware itself. So I do not believe this will be take much in consideration to be a very specific analysis. But in the software part, I believe quite firmly that there will be some actual available information for the current analysis and the next analysis, because we are looking for something different, something not usual for the current analysis, let's say, for the current status that we have already aware of. So I believe that you see something in this direction, but technically I could not elaborate it more than it. That's not for the moment.
But it may be an important input. Of course, probably the tracking people know about this, but depends on how much pressure and the experimenter has and how much interest it has on this. It may be something interesting. Okay, I don't want to monopolize the discussion here. I know that there's a line of people waiting. I may have a few more questions, but maybe I will get on one last question on your analysis. Sorry, because I have to go through my notes here. So maybe I will join two questions in one question. What is the level? I think you don't comment at the level of the theory uncertainty on your models that you have for because you basically rely only on MedGraph and for your estimatives, right? I think that for the work for the thesis, this is fine. So now I am going my curiosity here only. And are there any plans, for example, to look at other possible generators and even changing I don't know what you can tune on the Monte Carlo to have an idea of how good or how bad are the modeling now? For example, let's go from something simple like which probably is not the case here. What we usually do is we can change the renormalization scale or PDFs when we do the electroweak measurements, but this is a search. And how I mean, how confident you are that these models, because it represents what you're searching for, because this is really something that some type of analysis where you rely heavily on what the models are giving to you, right?
Yes. So this, how can I answer this? Join something that we didn't dedicated much effort on looking at it. So basically have the math graph, and we have been using it for since the private production, now more recently to the official production, that is the data that the Monte Carlo that we use it for the analysis and some extra work. So directly in the question, I do not have a clear picture on this. If there is idea of having different generators, I would say no for the moment. I believe that for at least this part, this analysis specifically, there will be other pressing needs before the MetaGraph for another generator on it. So I would believe that should be not be taken in so much serious consideration before we solve it. Different ideas, for instance, the spiking filtering, dedicated high level trigger path. I think before it, I don't know if a new generation or how confident the generation are dealing with our analysis, something that will be in the discussion. I believe that this will be the best answer.
Okay. Yeah, because for example, on your ABCD method, you rely on the PT cuts and so on, and this may that may affect some migration between the signal and control region. But I mean, this is beyond this. Just a last comment. What I missed on your final presentation, on your final conclusions, is really a consolidated table of the systematics and how this compares with the statistics that you have. I think you go term by term, but we have to do this, I mean, on the border of the page to see how much, and assuming that all your systematics are uncorrelated, right? And which I think they are, but maybe I'm not an expert on this analysis. Maybe there's some correlation on some terms that you may have. I think you don't have to go through this, but probably you may mention this, and that would aid the reader on getting the message. I will stop here, Karsten. Thank you very much. Sorry for taking that long, but
Sem problema. Muito
a few
obrigado,
questions.
Marco.
Yeah.
Muito
And
obrigado, Marco.
congratulations again for your work.
Okay. Okay, next on my list is Marcelo. Why don't you go ahead?
Okay, so let me turn it on. Can you hear me? It's okay?
Yes.
Loud and clear.
Yeah, okay, very good. So, well, let me start thanking for the invitation. It was very nice to go through this work. Thank you, Karsten. Thank you, Thales and Albert for the opportunity. Well, in general, was a very robust work. Really, a lot of stuff. Really, 200 pages of text is really shows how much work was involved in this thesis, and so I like to congratulate Thales, Karsten, Albert for the work. Is really something very detailed and very well built. Maybe the only I think the text was very well written. I don't have much to say about any correction and things like that. Maybe just very small things that you can catch up. Maybe the only criticism that I would say about the text is that's actually too long, right? Maybe Thales could be a little bit more objective and more specific in some point. Like just the CMS part has 50 pages. I understand that maybe the idea is to have like pedagogical material for next students, but maybe some of these things could go to some appendix or something just to make the reading of the text more easy. But anyway, just a detail I think was very nice. So I'll probably just make few questions, more general questions. Since this is a thesis defense, I'll try to, in the good sense, provoke Thales to defend his work and his thesis with some very general questions, and I'll leave maybe next to me, Tiago will have more, as Marco did, more specific and technical questions. So just to start, I'd like to understand better. So you have these two topics, let's say, more or less independent topics in your thesis, the luminosity measurement and the monopole search. So how did it happen? I mean, you have like a kind of service work to the collaboration that you you decide to do this Z counting, and then you came up with, but there is not much relation between them. So just to understand the context, how you came up with these two separate topics.
So this was, as Carsten mentioned briefly in the beginning, the first line of the main analysis was different. So at this point in time, they also presented to us this accounting opportunity, which, if I remember correctly, is someone that Carsten had known from the past, right? I think Andreas has a common connection with Carsten, if I remember correctly. So this work was presented. So this was start of let's say the PhD work was this accounting, which is a service work at some point, because it's also part of DPR and so on. But on the other hand, is analysis itself. So there is even an analysis note, a paper from the method. So it's kind of a second analysis. So since we spent a lot of time was spent in this analysis, and quite interesting for a lot of reasons, especially for the results. There is a lot of results that can be performed, even that are outside of the thesis, because it's already too much pages on it. So some of the results were not present. So for instance, we can use it to spot different calibrations, different changes in the detector just by looking for the rate between the Z and the luminosity directly from as a function of the rate of luminosity. So this is a very interesting analysis. So I think it was quite relevant, quite interesting to put it in on the final work, because also observing some students from here that was also part of our previous work that do the same thing. So I think it felt quite interesting. And then, of course, the analysis is something that should be the focus of the thesis. So just the idea is to basically write about all the work that was done during this PhD time. So I think this is more or less the answer.
Yeah, so the monopole search was decided after you had already started the Z counting.
Yes. So it presented itself a little bit in the future.
It was late in your PhD that you decide to do this. Okay, and this method of counting measuring the lumens, that was something that was not done in CMS before. You were the first one to propose this kind of method. How?
This method is it was also, if I remember correctly, was started also in lab for the different. I think I have some slide here. Let me just change it. So this is not the original idea per se. It was some studies done in the past, because I mean you do not suffer for machine parameters, for instance, we rely only in physics. So this is quite an interesting thing to do. So it has some results in the past. I probably have some in the backup. Yeah, so that is the idea. So to be also using, for instance, the Baba scattering in the past rather than to the Z into muons. So the idea is not that new, but the implementation in Hadron Collider is become a little bit more challenging because of its proton-proton collisions. So it's way more complex than electron-positron. So this idea was developed and implemented in run 2, where you had most of the documentation of the method already. And for run 3, the idea was to expand it, let's say its functionalities, especially in consideration that you have more parallel, that you have more data taking, and that is the high loss LHC on the corner. So this is something that to be used, that is complementary at some extent. But the idea that this, let's say, the main basis of the idea was not new at CMS, not even let's say, for instance, so something from the past that was implemented at CMS for this current let's say collision program for run 2, run 3, and so on.
But you were the main driver of this this approach in CMS, let's say. Your work was kind of something that you really brought to the CMS experiment as a proposal.
Yes, was not brought by me. It was something that was discussed in the past, I think in the time of run 2. So there was some students that was part of this work before. So I basically entered on right on the beginning of run 3. So where some of the students would be left in by different postdoc positions, for instance. So it was more like a person responsible for run 3. Or be more like in this sense that someone that brought the idea for the analysis. Because I mean, if you take the documentation, if you take the framework itself, it's a whole lot of analysis. So something that if you do it completely, it would require 2 theses basically, because it's something very, very extensive, a lot of details, a lot of uncertainties. So it's quite interesting at this extent.
Okay, nice. And well, I'll stay in this topic before I move to the monopole. So for the, let me just check. Yeah, so now that you did this, so what's your expectation for the to use this in the future for the high luminosity, for instance? Do you think that is will be a good strategy?
Yes, it's quite useful. If I brought you, for instance, these slides these plots that you are seeing. So this is basically one thing, but the CMS, since it has a lot of different luminous detectors, there are ways to produce these plots. For instance, to take one luminous detector as reference and produce the ratio between the other ones and this, and you have a plot similar to this, but a little bit more with more information. So this plot is quite something that is, if you attend the luminosity meeting inside CMS, plot that is every time being discussing to be approved, to be improved, to change the approach and so on. So it's a plot that brought a lot of effort in it. And this account is a very good way to cross-check all of this information with an independent method, because in the first scenario, in the standard method, you're always relying in one luminous detector as the reference. So it's a good reference, not a good reference. It's the best reference. It's the best reference for this period, but not for the second period. So this is a forever discussion. It is accounting something that tell me it's the boson decay in 2 millions. It's that it's a reference itself. So this improves a lot on the discussion and can be used to have this kind of extra and complementary cross checks that could be not entirely responded by this cross check if with the luminous detector itself. So something that has a lot of value in this. And also in order to provide, if it's also one of the objectives, provide independent luminous measurement, because these basic falls in the same idea. So if you're doing with the standard methods, you have a reference. This reference is good, is not good, could be better, could be worse. This one is better, this one is not the best. So you have to have a reference, and you don't know if how absolute this value will be, how good this value will be. But this accounting is something that's not related to the data taking, to what we are doing, because it's a Z-boson decay in 2 million. So even doesn't care if you're looking through Atlas or CMS. So it's the physics itself. So this is also a method that could bring a lot of things in the table in this scenario as well. So basically a cross check, a good cross check.
Okay. But do you think that your work consolidate this cross-check in CMS for the future? Do you think it's something that you were convinced that the collaboration that should be used in the future and things like that?
I would say that is in this way because part of my work in the run through was able to get this in two different ways. The first one is something how quite in a real time thing. So, for instance, if you use, for instance, the online data, you can do observations, you can do evaluations on the method quite daily because as soon as the run is finished, you can quite immediately have a follow-up on this. This is quite useful if you're doing luminous checks. And the second one is this one done before done just for the collection of the best measurement. So let's say we wait for the end of the run. You have the data quality monitoring and you do the results based on this. And that's it. So now we can also do it for different luminous detectors. So I can brought each one of the detectors of CMS and produce some results, some evaluation. And also it's possible to do it in a more, let's say, granular way where you can, for instance, they have this detector, they have this version of the tag. Oh, they are good, great, let's can use that. But in 2 months in the future, no, this is not good. We have implementation, we have an update on this, and have a second tag, and you can have the same evaluation for these tags and compare between the two, compare between different luminous detectors. So this something that is independent of all these detectors, and this could be done for a variety of cross checks. So this was something that was part of my implementation during the PhD. Was not present in previous work, for instance.
Okay, very good. So let me just go now for the monopole part. So I would like you to discuss, Thales, a bit the motivation for this work, right? Because as you put in your thesis, this is something that was proposed many years ago, right? In the beginning of the 20th century. We had a lot of work, a lot of, you showed even experiments that are dedicated to this search and everything. So how you would justify this search that we still need to search for it? And I mean, in terms of understanding of this possible particle in terms of theory, I mean, do we still have arguments to keep looking for it? How would you defend this search nowadays?
Yes, nowadays is something that changes the question quite interestingly. I think there is two ways to look. The first one is probably the most, I would say, philosophical, logical way, which is physics and physicists love symmetry. So if there is something that's not symmetrized, there is some asymmetry. We have to understand why this is happening, or if there is a way to symmetrize it. So I think the Maxwell equation, which is a foundation of the electromagnetism, at least the classical one, something that have a lot of, let's say, gravitation around it. So everything that you can change this change a lot of things. So this will be, let's say, I believe, motivation by itself, because if it says that we are not observing any kind of divergence in the magnetic field, why not? A lot of questions that can arise from it. And if you at some point in time change this answer, change this equation itself, you change a lot of things. So this is something that is quite relevant and you impact a lot of different fields. If, for instance, in the scenario that there is some kind of magnetic charge or something very close to this semantics. So this is, I believe this is motivation enough in this scenario, because it's not something that is, let's say, part of a very specific model under a very specific set of conditions. Only if you consider that this kind of theory is true or partly true, so it's not that specific in this scenario, or produces or proposes let's say, things that are even more exotic in the scenario, like composite particles with multiple quarks and so on, something that is specific at some extent. So, but it does not fall in general searches, like for instance dark matter candidates and so on. So it does not have the same appeal. But building on this, you mentioned nowadays. So nowadays, I believe we are searching for new physics. So new physics could present itself in a lot of different ways. So I think the best you can tackle all of these possible scenarios, the higher the number of scenarios that you can attack, that you can exploit the best for the field, let's say the academia, the scenario itself. So I believe these are two ways to answer this question.
So theoretically, you think there is still room to expect the existence of these monopoles?
It's theoretical, purely theoretical. I do not know if I can say this. It's something a little bit. It's something that provokes a lot of impact. So something that is quite not so easy to propose because impacts a lot of different things, ideas, and so on. But on the experimental point of view, we can open space for particles with magnetic charge that probably not a magnetic monopole, but some other, let's say, exotic particle that we discover in the future that for some reason that we do not have any idea at this moment have magnetic charge, but not necessarily related to the divergence of the magnetic field that was proposed by the Maxwell equation and so on. So could also open up this space in this direction rather than to be a specific one. So for instance, Atlas in general have the research in magnetic monopoles together with the highly electrical charged objects, for instance. So something that is could open up different avenues on the research.
Yeah, so going this direction, experimental point of view now, because you mentioned you showed in your thesis in the end these results from Atlas, and you mentioned many times during the thesis that because Atlas does not have this filter, so it is ends up to be more sensitive to this surge. So this result from Atlas probably came after you start your thesis, and so how do you also, from experimental point of view, you justify your search? Because if Atlas, let's say, if you have already some results that are more sensitive than yours, of course you can justify in many ways that I couldn't I couldn't know that my measurement would be less sensitive, or I didn't know that this measurement wasn't public at the time. But given this scenario now, how do you justify your specific search?
I believe in a more probably the most easy way to answer is if Atlas produced something, CMS have a good motivation to produce the same thing in order to compare how both experiment explores, studies, understand the same thing basically. But the results from Atlas also induces some kind of extra motivation to CMS to pursue it. But the limitation limitation present in CMS degrades a little bit this idea because like I do not have the results of Atlas here directly for a lot of reasons. But for instance, they have a signal efficiency that could reach 60% when you have barely reached 5%. So this is something that is quite let's say remarkable difference with a factor of 10 here and there. So, but even if you're able to produce results that are somewhat competitive with what Atlas produced, with let's say a most suitable experiment to do it, I think this is quite interesting. Because you can also show uh, let's say how CMS handles with this and produces results that are somewhat comparable to Atlas, even having some actual limitations in its analysis. I think this is probably the main thing. And it can also open up explorations, for instance, for heavy ions as well, but this is a second topic.
Okay. And just now, in terms of the CMS context, your search was the first one, or was a different one? How do you uh, how is it inserted in the CMS context?
So there was a search in run 1. There were some developments that were done in run 1 rather than run 2. So this is basically the continuation of this. But for this particular status of the analysis now, we implemented a different strategy that was not present in the past. So the idea in the past is that we're basically looking for signals in the eCal, and that's it. But we had a lot of limitations by the spike filtering, by the nature of the monopole itself. So the run through, the main idea was, okay, if you cannot trigger directly, maybe you can trigger on the missing a trigger efficiency. So this is something that's new, it's brand new for the analysis. So the motivation started in run 1, it's continuing in run 2, and the idea of my work and the idea of the current status for the analysis is that these two strategies that at some point complementary and could help to increase the sensitivity. So if you're not able to do what Atlas did, which is basically triggers directly the monopole because of its based on how it interacts with the depth detector, the tracking, and also the eCal, the electromagnetic calorimeter. So if you cannot do in this way, maybe you can do a different way, which is, since it's not there in the reconstruction at least, we can find, for instance, through the vicinity energy. So it's a different approach in trying to answer the same result. But in the context of analysis itself, excluding, let's say, the point of view of Atlas, this strategy of including vicinity information, triggers, and so on are brand new for the analysis. So this is something new and probably should be, since there is no, let's say there is no, this not dedicated effort or not for this day, a dedicated effort in the direction of the development of a high-level trigger. Maybe this would be the way to best deal with the analysis. So if you cannot remove the spike filtering, may develop a way around it to study the same thing. So if you bring Atlas back in the table, the idea would be reach a comparable result with a different strategy, kind of. Because you're also relying triggering something that's not in the event itself. Expected to be in the event, but it's not. So it's something that Atlas didn't do, for instance. But, well, they don't need to do it, but different strategy to look for the same result.
Okay, very nice. Let me just, I'm already in 20 minutes here. Let maybe just two more specific questions, maybe some curiosity. So you rely heavily in the energy loss, right? In the of this particle in your detector. And then we have the bat block curve that is known for the electric part, right? And then you I think it was, I don't know, slide 10 or something, where you show then this model for the if you consider the monopole, yeah, that there, I think you pass it before, yes, there, where then you consider the magnet monopole effect in the energy loss. So can you comment a bit about this? So how reliable, let's say, is this calculation or this proposal, since of course this is not, because the bat block has a lot of empirical information, right? You rely, of course, in some theory, but you rely also in the experiment. Here you don't have, of course, the handle of the experiment, so the measurement. So how reliable or how is this built, and how confident we can be in this proposal of this equation?
I think this could be answered in two ways. The first one would be the simplest one. So it's basically, if you take the standard bat block equation, and instead of having the electric charge, you place the magnetic charge, and then just brings back the equivalence. So you already see there will be a huge difference between a particle with electric charge and a particle with a magnetic charge. So this would be enough to say that there will be some difference, a very high difference, but this will not answer how confident we will be that this difference is well modeled, or at least how good is the measurement of, or at least the estimative of this difference. So there is different ideas for implement this equation, which is the true correction that was briefly mentioned. So this will take in consideration, for instance, higher magnetic charge, which because make this equivalence even higher. You have some particle with 5 magnetic charge, this equivalence would be way through the roof. So this would be some challenge to deal under this scenario. So how confident it would be? This is a thing that the best sensor to this will require a little bit more effort in looking on the Bat-Buckle equation directly, because there are some extra correction, there are some extra implementations, considerations that was not part of, let's say, the standard one for just electric charge. So this will require a little bit more effort, but I would believe that just by the difference, just by the equivalent itself, which is quite significantly around 68. So a part of magnetic charge will correspond to around 68, a particle of 68 of electric charge. So only based on this difference, this will lead to very different results from the Bat-Block equation, and this will be translated to very different, at least in intensity of interaction or strength of interaction that will be translated in the detector itself, depending if it's Atlas or CMS for in this scenario. There will be some difference, but probably not as big as the difference between a particle of magnetic or a particle of electric charge. So I think that just by this equivalence, that will be that will be arguments enough in the fact that you see this difference in, let's say, play out in the experiment.
And also still in this question, but from an experimental point of view now, because do you have any support, let's say experimental empirical support, that how this detector would really react for such a high charged particle? I mean, because usually we deal with very low charge, and then if so, do you have any experimental handle on how these detectors would react to a 68.5 electron charge particle going through it?
So this is interesting because even that this analysis didn't originate in run 2, it's quite new at some point because we not have past analysis of high ionization particle or particles in this scenario. So a lot of this answer will be something that will need to be developed because it was not present before, not done before. So something that is need a special attention to it. So, but in the sense of the tracking, for instance, the trajectory itself will be surrounded for extra particles, and this will cause a lot of uncertainties around it because we have to account for this. And probably this will lead to in the ideal world that the analysis will be very easy to tackle because they will be very different from anything that we already know it, especially in the tracking context. But this will come at the cost that you have extra interactions around the trajectory itself. And this will be not something that was, let's say, thought of when the CMS was developed. On the other hand, on eCal, it's basically something that will deposit its energy very fast, very quickly, especially its kinetic energy to be considerably lower than the total energy because the mass of the monopole is quite significant. So this will to be translated just by a compacted energy deposition instead of, for instance, a showering through the whole calorimeter like some particle decay in a electron pulse pair will do. So this will be quite a way to see it, but in the context of CMS, this will be very similar to some malfunction in the crystal where for some reason only one crystal will be firing up for the equipment problem for something that's not related to physics. So this is the problem in it, but will be the main thing will be quicker for the ecal. There will be a very specific kind of pattern, and for the tracking, you have a very specific kind of pattern as well, but you have extra interactions around the trajectory. Where for ecal, you have something that is very localized, very concentrated, which is very unclear, very uncommon if you consider other analysis.
Just my my final question, so I don't also take too much time. But so now for the conclusion of this monopole search. So how do you let's say, evaluate, or how do you place the impact of your analysis in this search? So you would say that now we can be sure that if the monopoles exist, they must have a very high mass, or so. What is the impact of your analysis? You think you evaluate for the monopole search?
I believe the most of the impact to be related to a strategy to deal with the main limitation of the analysis, because the whole motivation behind it is quite clear, but we stop at the limitation at equal, and it will be passed on the trigger. So I think the main impact would be, okay, there is a way to work around it. If you cannot trigger directly, you can at least look for in the different direction, build a different strategy, and this will be part of the analysis going forward, because it produces a high sensitivity, and you also can use it. Can be used for the different probes. For instance, if you want to different magnetic charge evaluations in the future, it's something that is not be sensitive to it. For instance, when you have the regular strategy, which will be just really looking for equal deposits, as soon as we increase the number of magnetic charges associated, this equivalence get even higher. So this will lead to even more concentrated energy deposits that could be probably something that was not studied at this point, but at some point in time could reach a scenario you have zero signal efficiency, because all the pods that you have will be concentrated in one crystal, because your number of magnetic charges will lead to a high equivalence between magnetic and electric charge. So this will lead to basically the analysis to be not feasible inside the detector, because all of them will fall under this spike filtering. So this will not happen in the case of the missing HE strategy. This will be holding for any kind of extra magnetic charge that you want to add to probe it, because you are already relying the fact that we are losing the monopole by the trigger. So this is something that will be part of the whole analysis, at least in the current status where you do not have a dedicated trigger or a way to avoid the spike filtering. So this is something that will be part of it, and that is probably the best way to work around it.
Okay, very good. Thank you, Thales. I think that's my last question. So thank you very much again, and congratulations again for your work.
Muito obrigado, Marcelo. I think we stay in Sao Paulo, and next one up is Thiago.
Hello, can you hear me?
Yes.
Yes, perfectly fine.
So, first, congratulations, Thales and Carsten. I also agree with the others that the text is a bit too long and in need of a bit more of English revision, but I'll just send my comments on that afterwards. Since I am in CMS, of course, I think it falls on to me to ask some of the detailed technical questions. So I'll try to focus on that, okay? Okay, first, in page 22 of the thesis, you really say, you say the first thing that I found a bit interesting, particularly the fact that the magnetic monopoles are accelerated along the magnetic field, unlike electrically charged particles. But it wasn't clear to me, and I would like some clarification then. You really mean that they gain energy from the magnetic field? They are not only, their kinetic energy actually increased? Is that what you're trying to say there in line 1961?
Yeah, so this is something interesting. It's a study that was done but was not part of the thesis. So exactly in these lines, so if it's interacting with the magnetic field, it should gain some kinetic energy on it, and this is a fact. To have studies where this would happen. but you find itself in two different scenarios where you can gain some energy because it would be aligned, and there are the ones that could be lose energy because it would be decelerated by the field. So if it is in the opposite direction. So in this scenario, have these two ideas. You could gain energy at some point and could lose energy in the other scenario. So it's something that was done. We have a study on it. So you find exactly this. So we have basically a symmetric distribution around zero, around -1, around one, something very symmetric around zero. And exploit exactly this. So you could interact with the magnetic field and could gain some energy in this scenario. This is something that is part of the idea, yes. So this will be something, just a consequence of this interaction. And then I'm about to gain energy as interaction with the magnetic field.
Okay, so there are two things here that first, I think that if you this derivation, at least the general lines, should be in the thesis. And second, since you already open up the possibility of the magnetic monopoles being charged, wouldn't this actually open a third possibility of their detection? Because if they are accelerated like that and they are electrically charged, besides being magnetically charged, wouldn't they produce absolutely gigantic amounts of Bremsstrahlung? And couldn't you then trigger on this Bremsstrahlung?
But this in the scenario that the monopoles are electrically charged, which is not the case for this analysis. In this analysis, we're considering a particle with only magnetic charge, so with no electric charge. So at least in this analysis, there is nothing about this idea. So a particle with both charges would be something different. That was not covered in this text.
Okay. Okay. Then what else? When you discuss again, it's 50 pages, as Marcelo said, it's 50 pages of description of the SMS detector. And but on top of that, I feel that there are, I won't say missing, but I feel that you have to be a bit more careful in two scenarios, two cases. First, you're talking about two different detectors in a sense, because you're doing Z counting for RAM3, and but you're doing the monopole analysis with RAM2 data, right? And
Yeah.
the detector changed a lot. So for instance, you don't say anything about just as an example, the new pixel detector, right? Particularly, even in RAM2, we had the new pixel detector, but when you discuss when you put a picture, schematic figure of the SMS tracker system, you put the old pixel detector there in page 42. So this is just one example, but it will really beckon to go through the text and understand where the upgrades come in, and maybe make a note of that. Be more explicit on what you're doing. So page 42, you see there the pixel only has the 3 barrel layers and the 2 end caps on each side.
I think it's quite tricky because part of the analysis is with run-through data and also the secondary is run-through. So this is quite a tricky topic to address. It's also do not have this addressed in the title because it will be even more confusing because you would say run-through and run-through in the same title and will not be a combination. So this will probably bring a lot of extra questions and discussions around it. But this is something a little bit trickier.
Yeah, but something has to be done, right? You cannot just not do anything and leave it be. So I agree that it's tricky. Please try to do it anyway. Okay, what else we have here? On page 86, talking about the luminosity determination, you do speak a little bit about the the equation 4.5, you discussed a little bit about the luminosity for high pileup and the number of that it depends on the number of Zs that the high pileup runs and at the low pileup runs. But when you say that it has to be efficiency corrected, you didn't you weren't explicit about measuring the efficiency as a function of pileup. Were you? I at least didn't notice that at this point on the text.
Those of the high pileup conditions. Okay, I see.
You really have to measure the efficiency as a function of pileup for this to make sense, right?
Yes. So we have it this as, for instance, the plots that are in the also presented in the slides, where you can have the single efficiency, the single mirror efficiency, even the high level triggered one for each one of the fields, and this will happen if it could be done for different sets of fields. So for a low, if you have a low pileup, if you have a high pileup, so this is something that is already part of the work itself, but maybe some extra information.
I think it would be important to have it explicitly derived, because that, I hope you agree with me, that this equation 4.5 really is the heart of the luminosity the determination. So you really have to show that you control the number of Z bosons in both conditions.
Yeah, so a different way to look at this will be a little bit more, require a little bit more, let's say, imagination, or I would say. So when you did, for instance, this, let me just change the plot to give a little bit more context. When you change this approach to work with these plots, for instance, which is basically the main figurative merit we have. So the way that you can observe this, especially this ratio between the number of Z bosons in different fields, for instance, high pileup and low pileup, it is how this will be behaving. So, for instance, if you select a given data taking period, like 24 for some reason, and you see that that is the best luminosity measurement of it, we can tune this distribution in order to achieve where it's best aligned with, for instance, 1. And from this we can extract a number which is basically a cross section, but could be interpreted directly as the constant of the calibration that could be translated for different years. So this is a different way to look in this ratio, that you can be, and how they will be, let's say, translated in the measurement that you have. So you can tune this and get this ratio all the way to different data takings, for instance. So this ratio can be seen in this kind of plot. So if you use a different one, this distribution could be shifted a little bit upwards, a little bit downwards, depending on how you select it. And also, if you're dividing two ratios, a lot of the uncertainties are already canceling out because we are dividing the same thing, so we're not dependent on it.
Okay.
Back to it.
Let me look again on my notes. Okay, I think we really have to go. We can go to the magnetic monopole part now. If you go to page 126, when we start discussing the new track combiner algorithm, first a very simple question, and so page 126. Yeah. The algorithm begins by selecting a track segment and scans through all the other segments. What are you calling a track segment here?
Be the output of the standard CMS tracking algorithm. So we'll be combining all of them to form just a custom tracking, a monopole tracking, a curved tracking. There's different ways to name it. But it
Okay,
would be basically the output from the standard algorithm. That would be the track segment.
okay, so it's really the clusters.
It will be the track directly from the standard algorithm. So you take it as the way it is and combine it like a step by step in order to reconstruct the tracking of the monopole, where you'll be expecting some kind of curvature, which is not be possible.
Tracks. Track segments are tracks.
Yes.
Really? I mean, I don't see how this can work then. I would understand that this could work if the track segments were hits or doublets or triplets. But if they are complete tracks, I feel I'm completely lost.
Okay, it may need a double check on it, but this would be the idea.
Because I understand if it's the clusters, I understand if it's the hits or doublets or triplets, but they really have to be, they cannot be the complete tracks. Otherwise, I don't think this makes sense. But in any case, I have the interest. So this was the technical question, not the interesting question. You say that you scan through all the other segments, you do refits. How long does this take?
How long it take to take it this scan around other segments? To find something that I didn't dedicate much of my effort. So we basically have the framework where you already have this. Where basically the main idea would be extracting these different values of the fit parameters. As soon as we have the monopole track established, the main idea of this would be extracting these fit parameters, and if it passes, it will be a monopole candidate. If it doesn't passes, it's rejected by the analysis cut flow. So how much time is taking something that I didn't dedicate the effort to, which, and I will probably not have a clear answer to this.
But was it negligible? Was it something that you had to take into account while you were doing the analysis, or was it something that you ran in your computer like in 1 hour, more or less? Because if it's something that took 1 week, it's different, right? I'm asking this because tracking is hard, right? Tracking is the thing that takes more time in the reconstruction. So if you tell me that you're really redoing tracking, I'm interested in seeing this should have been a bottleneck.
I see it. Got your point, but something that I didn't explore that much in order to have a clear answer to it. Something, at least in the state that we use in the analysis, was something that was already present and just something that is part of it, and not some that was exploring to see if that is a way to improve it, that is a way to reduce time, increase efficiency, something that was not part of the effort, so I do not have a clear answer to it. I would believe it's something simpler because this timing questions on the analysis was not an issue, not at least not related to the tracking. So I would believe something that will not take that much time, but is to be an educated guess, not a final answer.
Okay. Then you, in page 150, you do a delta R in between equal clusters and these monopole tracks. And since these are brand new monopole tracks, I have to ask, did you remember to do the extrapolation of the track to the equal interface? Because if the curvature can be large as far as I understand, right? So you did, and I think that in the standard CMS software, this is done not automatically, but somebody already took care of that in the software. But here you're doing it manually. So did you remember to do that?
Yeah, so this will be a clear issue if we have some relevant significant curvature on the tracking, which is not exactly the case. I may have some results to back up this idea. Let me just reach it. to have 2 as an instance. So if you take this set of plots, these were basically the fit parameters, but I'll highlight this one. This will be the curvature of the trajectory from the monopoles, and you can see quite clearly that is something that is not that present. For instance, if there is plots that we have in not in the analysis, not in the thesis, but in analysis, if you overlay the data in this presentation, this distribution, it's basically the same thing. So the curvature does not play an important role in this. So it's something that will not affect this second level. And for it added support this, if the curvature is something that is very much different and it should play a different very different role in the analysis, that would be interesting to evaluate its power as a discriminant variable. And you can see by this that is not the case. So something that is very similar to let's say the standard data that we have or standard kind of particles that we're expecting. So the curvature itself is something that is not affecting, not play a big role in the analysis, even if it's part of the, let's say, of the nature, the peculiar nature of the monopoles. But for instance, if you are thinking on monopoles with some few GeVs of energy, maybe this will be a different case.
I see. Okay, thanks. Still on page 150, you go to the trigger paths, right?
Mm-hmm.
Okay, so you went with single photon and MET. First, did you check the total? Did you know that we have a total transverse energy path only based on ECAL deposits, the ECAL HT800 path?
This sugar path would be exactly what would be the idea, to have all the equal deposits.
Yes, so it's just like the regular HT paths that you know that you sum the jets, but and you sum the PT of the jets scalarly, but usually it's not done with the hadronic calorimeter. Actually, it's done with the jets, right? So it takes both, it takes everything. But there is a path called ECAL HT800 that does the same thing, but only sums ECAL deposits. This exists, okay, in Rancho data. Did you know this exists? Did you check this?
But this will be relying in the fact that the signal will be depositing its energy on equal.
Yes.
But we are in the scenario that we're expecting this will not be the case because the event will be rejected by any trigger that you select because of the spike filtering. Even for instance, the PF-MET trigger which shares some level 1 seeds with the single photon trigger, so they will be not part of the. They will be already rejected at level 1.
Okay, maybe at level 1, true, fine, I'm not sure. But if I remember correctly, by the way, parentheses, I remember correctly because at that time I was the Exotica trigger contact and I was the guy pushing for this path to be in, okay? So it's kind of a self-advertisement. But in any case, I think that at the high-level trigger, this path will not will take the uncleaned clusters, not the cleaned ones. So maybe it's useful. My only thing that I'm saying is just check that, please.
Something that was not discussed, but if the event's already rejected by level 1, that is not much we can do in the high level triggered scenario, I believe.
Okay.
I expect on triggered, but
fine. The second thing is that when you choose the particle flow missing ET paths, you went for the 200 or something PF-MET paths. But there are lower MET paths.
Yes.
PF MET no mu, PF MHT no mu at 110, 120. The only thing is that those paths remove the contribution from muons, which you don't have. So why didn't you use these paths
Yeah,
instead?
so this is a question that is very pertinent on the analysis. So the simple one would be you cannot use any kind of hadronic information because you're not expecting it, but there are a lot of miscellaneous trigger paths with low threshold do not have anything with the hadronic, so this would be suitable. However, I have two things. The first one is a little bit more technical, the second one is more physical. So the technical one would be the data scheme that we have for the monopole does not comprise such trigger paths. So if you go in the direction of, okay, should we redo the scheme to have these lower thresholds implemented, this will require the whole reprocessing of the run 2 data in another run reconstruction campaign, and this will be a little bit problematic in the context of the time scale. So this is the technical. Probably the physical reason would be since the cross section is quite steep, and we need a very significant difference in signal efficiency to see any kind of effect. So if you change the factor by the threshold like 20 to 20%, maybe there is not so much difference in the final result because the cross section is quite steep. So you need a very significant change in the signal efficiency, and we do not believe that this will be resulted for a trigger path lower threshold. But of course, this will increase the limits, but the technical effort behind it will be probably around unfeasible at this time.
Okay, I see. Yeah, that's a pity. But okay, maybe for hand 3, people can do it.
Yes, this is a question that we answered sometimes during the process. So
I can only imagine, yes. Okay, moving to page 152, which are really the cuts on the table. I see that you decided to cut on the EDX significance above 9 and F51 above 0.85. So first, there is no cut on timing whatsoever. You made the study, you did the study, came to the conclusion that it's not worth it. Fine. But where did these values come from, 9 and 0.85? I don't see any optimization.
okay, so these values came directly from the distributions of the discriminant variables itself, especially if you take, for instance, the DX. Let's go to the DX. So you can see quite clearly there is some kind of inflection point around, let's say, between 3 and 9, but probably around 9 or 7. So this was the main reason for the selection of these values. If you look on the data, there was some optimization, but these included unblinding the control regions to do it. But for the Monte Carlo, will be basically related to the shape of the distributions. So you can see quite clearly the difference that is, let's say, the two behaviors that are separated by a dead around 5. So if you overlay the data, you see there is something exponential decaying all the way to 3, 4 to 5. So this is where we trace the best value for it. And F51 basically follows the same logic, but this inflection point is not that visible. But we are basically exploiting the most concentrated possible energies that we have. So because this will mimic, at least this will be more close related to the monopole energy deposition, which should be very concentrated, not very sparse. That's basically the shape of the distributions.
Yeah, but
There was actual optimization on it.
From this distribution, I'm sorry, I wouldn't cut in 0.85, right? I would cut in 0.95, 0.99, right?
But that would be too restrictive.
Yeah, but look at the spike on the right.
No, it's quite significant.
Okay, what else? Then in table 16, page 156, you go and discuss the expected PF math for each category considered in the study.
5, 6, yes.
Yes. And I didn't understand. You have missing ET when one of the reconstructed monopoles fails to be found as particle flow candidate. Fine. But how come when you have, so the third line, when you have two PF like, how come they are, you still have a high PF met, 500 GeV?
The result a little bit more general in order to see if we are able to capture PF match from the PF match trigger. So this is a little bit more general than appears to be. But the idea is that if the monopole can be part of either a PF mat candidate in the form of, for instance, electrons for particular reasons, and also could be part of the PF mat because will be not associated to any PF mat candidate. So to any PF candidate, not PF mat. So to any PF candidate, and they will result in also PF mat. So this is something that we can, that is some idea in the direction that you can trigger by having the monopole as a PF candidate and also having the monopole outside of a PF candidate, and you have some considerable PF mat. So this is more in this scenario should be more a supporting study to make sure that you can use PF mat triggered, especially because it has a high efficiency, so there is extra motivation to do it.
Yeah, in any case, yeah, that's where the efficiency of the trigger is lower anyway. Okay. Okay, yeah, those were my basic questions. Then I have a lot of comments on the text itself, but these I just send to you and Carsten by mail. I have nothing else, so congratulations again, Thales, Carsten, and
Muito obrigado, Thiago. Okay, if there's nothing else from Thiago's side, then we can come to our representative from Rio, and I would ask Murilo to ask his question. Murilo?
Okay. So first of all, thanks for inviting me to be in this jury. So Karsten, Thales, thanks for that, and Albert. So it's well, to be the last, it's always hard because I had some questions that were already asked, but I hope that I can contribute to this questioning. So to begin with, I think that the work was quite solid. You have two I mean, you have basically two data analyses. One which is related to luminosity, which is very important for the experiment, and the other one which is a search for new physics, and that is those are very interesting, and the text is very well written. So in general, for the text, I also have a few comments on the PDF that I'm going to send you, but I maybe I can give you a general comment that I think that should be it could be useful to have a final conclusion chapter where you list the final. I mean, because you finalized with the search, and that's the end, and then you have the appendixes, I guess, after that. So I guess a final conclusion would be useful. And maybe I'm trying to use the slides, but maybe we can just go very quickly to, since you have your PDF there, go to page 89. I know that was already asked by Marco, but I wanted to confirm because I also agree that was not very clear about the the mass model. I understand you have a resolution model, which is this Gaussian, but what about the Z? What you I think it's not Z, but you just have the Z pole here as your signal model without the resolution Gaussian. That's my question.
So the idea is that will be just the convolution between the Monte Carlo template that we derived, which is based on Drarian that has the z decay into muons, and be convoluted with the Gauss function in order to better describe the z peak.
Okay, so you have a Monte Carlo template.
Yes, the
That's
template.
not shown. That's not shown, right? Or it is shown somewhere.
Probably it's not. Yes, probably something that is. That
I
is
think
the
that's
explanation.
probably
Yeah,
what.
I have a Monte Carlo template that we use to model the signal.
Okay, so okay, now it's clear for me. Yeah, I guess a comment here could be useful. Now let me check here. Now in page 9.4. So yeah, so that's, I just want to check if that's a typo or if you really do it in this line 3729. You have a spatial separation of delta R less than 0.8. Is that because at some point you said you had the opposite? Is that correct, or it's greater than 0.8 here?
I mentioned that was probably a typo. I'll have a double check on it, but it should be higher than this if it is 2 muons. The Terfanazi boson should be higher than this. Yeah, so probably it's a typo. I can have a double check on it.
Okay. Yeah, because I mean, unless you had the boosted Z, I guess, if you were.
No, I think it's not the case.
Yeah.
It not be the case, yes.
So since we are now discussing, I mean, this delta R between the muons, I saw that I mean, is there any studies concerning the dependence of the luminosity with respect to the Z momentum, transverse momentum? And the reason I'm asking, I know that you have, I mean, you're basically, you have all the data-driven methods, which is very nice. But there are, I mean, the measurements you have CMS, Atlas, LHCb, you have, mismodeling in different regions of ZPG. But was wondering if that's something you checked, if the ZPG selection, if you could have a ZPG selection bias.
Yeah, I said so. Currently, you just have a lower threshold cut on the boson PT and also the muons. But a study regarding this dependence as a function of the moment of the Z, I think, is something that we didn't consider at this moment. So something that was not part of, at least not part of this work, especially because there was not so much time to dive deep on the uncertainties, because I mean the run is not even finished. So something that is probably belongs to the next steps, but something that for the moment was not there was not efforts on this direction.
Okay, no, that's fine. Maybe now I move to your slides. But still in this luminosity studies, in slide 11, you mentioned something that's very important to define in the luminosity calculation, which is a visible event. And it was not clear for me what is a visible event for you at CMS.
Not very sure about the visible event idea. So
Well, just to clarify, you have a visible cross section.
yes.
So when you say visible cross section, for me, it means that you produced particles. I mean, you have some particle production, and that was visible in your detector, right? That was detected. Usually, you have some requirements. For instance, you mentioned at some point in your thesis about the luminous detectors, where you have a visible definition, where you have a triple coincidence that that you have this. You count how many times you have this. But here, I think it's more like maybe a vertex reconstruction or number of tracks that reconstruct.
In this scenario, I think that the visible cross-section will be more related to how we are measuring the collision rate, that is basically this R, how this is evolving with the time. So different luminous detectors employ different techniques to have this rate measured. Let's say the best one is selected to make this calibration, but on the context of visible event, I don't think I understand fully this idea, but this divisible cross section.
What is an invisible cross section then? If you have a visible, then you should have an invisible.
Yes, but in this scenario, the visual cross section will be more related to some calibration. It's something that you can calibrate and use it, calibrate it from the luminous detector, and you use it along the whole year, for instance. Say this is the scale of the luminous that we have, that we derive it from, for instance, a very specific field for this particular purpose. So this is more in this calibration constant kind of application rather than to something that explicitly makes reference to a physical thing. I think that would be more in this scenario, some calibration, some constant, some scale that you can use to make the measurements of the luminosity, rather to something that you can, let's say, see or not see. I think that would be more in this scenario. For as a curiosity, probably the first time that I heard about this question of a visible event in this scenario. So just in general, just interpreted the visible cross section as just some calibration constant, some luminous scale that is part of the measurement itself.
Okay, yeah. I mean, I have, okay, this is a difficult subject maybe, but I had another idea what does that mean. Okay, maybe we can move on to slide 16. And so now you have this distribution, yeah. So this is interesting. There was also a question, I guess, also by Marco. With this trend that well, I'm not sure if this fit is. I mean, you have a band, but is it something that I mean, how do you do? I mean, first, how do you do this band? Is this taking into account correlated error? I mean, did you do this band yourself, or that's something someone did? Just to check.
You mean someone that did not stand, so this is part of the fit, and the errors would be statistical uncertainty based, most related.
Yeah, okay, but yeah. So one thing that I noticed is that you see that you have, it seems that you have like read periods where the cross section is going down. Sorry, the cross section is going down, then you goes up again, and then it goes down, then goes up again. I don't know if that's something that my eye wants to see, but let's say around 9, and then again around 11, and then again around 12. Is that something you looked at? If I mean, this period, I mean, when you reach this luminosity, you had some kind of calibration, calibration update or something that happened during this before these these changes that are not very smooth?
I would say that this distribution fluctuates quite a lot around, let's say, the unit, but there is a general trend that this ratio is decreasing as we're increasing the instantaneous luminosity, and I attribute the different, let's say, fluctuations as a part of statistical thing, because we can see already, we can also see it in the beginning of the distribution, where you have even fewer events, even fewer measurements that you have, let's say, to the middle to the end. So I believe that is something just more statistical fluctuated associated with, rather than to some general systematic behavior. But the general trend would be that this ratio is decreasing as we increasing the instantaneous luminosity. And as already we discussed, this plot will be way more interesting if you have extra plots, extra data, and also have the dedicated low power data set, which presents a very different, not a very different, but a little bit different behavior, and these make a good comparison. So probably there is no such systematic thing in the luminosity that makes this fluctuate, make this fiducial cross section fluctuates around the unit. For
Okay, so
instance, between
what understand that when you have this, I mean, you have regions where you have a smooth trend, and then you have 2 points where you have a very big difference, very big difference with a not smooth. So my understand is that from there is no change in the detector or in the nothing that happened that explains this. That's only statistical fluctuation, right?
yeah, there will be no difference, that will not change that will make the difference. This will be more preeminent if you take, for instance, the next slides. Then you can spot differences in calibration and so on, but not for this scenario.
Okay, now, yeah, so that's very interesting for the luminosity, and then now going to the search for monopoles. I also had a question about the Beth block equation. So maybe you go to slide 24, where you see this plot you have for simulation. Yes. So I mean, basically, yeah. So basically, this plot you run your Monte Carlo, and then you get whatever it says that you should have if you have a high ionizing particle with with the monopole with the monopole characteristics. But so my question is there any other models that can include other interactions with matter other than the ones that included in this Monte Carlo?
So the part, the part of interaction will be the ionization, also the pre-production, and can also include the Mistral. But the ionization would be the main driver of this interaction, so it's the one that was focused on for this work, and probably most of the work related to this. I think this is in the line of the question that you mentioned. So
Yeah, if the yeah, maybe I'm not an expert on this. I'm just wondering. I mean, you have a model, so this is model dependent, as far as I understand, right? But how my question is, how model dependent is this search? I mean, is there any other reason where you could include, I would just say like strong interactions, or not? I mean, there is no reason to have a magnet monopole with strong interactions.
okay, so this model considers that the monopole is a heavy elementary particle, which is also stable, which produce a little bit more different behaviors in the detector. So for instance, that will be, let's say, not absorbed by the detector. So in theory, you can open the CMS car and find monopoles there, but this is another story. But if you consider extra interactions, the monopoles would have to be modeled differently, for instance, as a composite particles, which is not the case for this work, and also I think not the case for Atlas as well. So I think this scenario is not present. We are more in the line of direct monopoles, electroweak monopoles, which is basically elementary particles, which are stable but heavy. But there are some more, let's say, theoretical proposal of monopoles as a composite particle. And this will lead to a different modeling and probably a different way to see the detector. But these, as far as I remember, have mass ranges that are way beyond the current reach of LHC or even the FCC. So I think this is a question that, for the moment, the answer will be okay. There is no motivation to model different monopoles. It just make consistent with this heavily stable elementary particle that will be mainly interacting through ionization, and will be also, for instance, not absorbed by the detector. I think this will
Yes,
be.
No, thanks. And finally, I have a final question on your efficiency tables. Now I forgot which slide. You had a slide with the efficiency, relative efficiency, where
Yes.
you and Thiago were discussing, but since I mean his CMS, I didn't follow some of the details. But maybe I should ask a more general question here. It's clear that when you look at this, your trigger is removing most of your events to begin with. So my question is, if you didn't have the trigger, were these events removed by the trigger? Would be removed by any other offline cut, or the trigger is really something that is killing these events? Is it clear, my question? I mean, these events that the trigger not selected are events that you could, I mean, you wouldn't be able to save even offline. I mean, that they have character, they are too much, they're too background like to be selected.
So the idea is just, okay, let's consider that we do not have trigger in the analysis, or that trigger is 100% efficiency. So this will lead, if you probably, there's a little bit about tables to have a little bit more values rather than distributions. We'll find something that will be similar to this. So if you take the whole analysis without the trigger, for instance, you see that the signal efficiency will increasingly sharp around 30%, which is based a factor of 10 that we currently have. So if you take, for instance, Gaussian spin zero, this could even almost reach 6%, which is, for comparison, is more or less where the signal efficiency of Atlas in this analysis is located, around 55 to 6%. So in this scenario, the line of thinking would be that if your trigger is close to 100% efficiency, or not that impactful, you have a signal efficiency that is very similar to Atlas, and then if you're okay, with these two results in hand, you can also think, okay, how many events are being treated as a nickel spike, or in other words, how many events are being rejected, and then this will lead to the factor of 10. So basically, for every 10 events that should be available for the analysis, if the trigger is not a big problem, we are keeping just one. So the relative efficiency is a way to see this, because basically the trigger efficiency does not even reach 10%, which is a factor of 5, 6 to 7 below what the signal efficiency of Atlas is. So this is already quite relevant. But if you remove this, the high level trigger you consider with a very high efficiency, for instance, in the context of a dedicated trigger path, the signal efficiency will increase sharply around 50%, 55%. So this will be a significant and a quite remarkable improvement on the signal efficiency of the analysis. I think this is probably the answer. There is a study on it on the thesis. I brought it on the slides.
Yes. No. That's clear. Yeah. No. Thanks a lot. That's very interesting.
Also,
Um,
have this, for instance, If you remove the trigger, you can see how much more populated would be the signal region. Just a quick visual comparison. So if you take the right side with no trigger, how many more events will be present in the signal region in comparison what is current present with the overall of the standard analysis. So this is also a second way to look at. But also the relative efficiency gives you an idea of how efficient are the offline cuts of the analysis. Tracking, clustering, and so on, for instance. And you can also build on top of the discussion from Thiago concerning the thresholds of the trigger. So if you take the PF the trigger the energy requirements of the standard strategy, you can see that is 90% efficient, so do not lose a lot of events. But when you switch to the PF match strategy, you can see that the requirement of the vicinity information quantity plays some significant role, around 45%, 50%. So this is also a significant source of inefficiency on the analysis. So if you're able to lower this threshold, this efficiency will likely increase.
I see. Oh, that's very interesting. Okay. So actually, I had other questions that were already asked. So I guess I can finish now. And thanks again for being part of this jury.
Muito obrigado, Murilo. I guess that concludes the official part with the questions, if there's nobody else. Betty, tá me ouvindo? Concluímos a parte oficial.
Sim, tô ouvindo. Eu vou passar vocês para a sala remota. É
Tá
só
bom, muito obrigado.
nada.
Então, essa deliberação demoraria mais ou menos quanto tempo?
Não sei, não tem como precisar, mas se você quiser ir tomar uma água e ir ao banheiro, acho que dá tempo.
Exatamente, essa é a ideia. Obrigado. Vou fechar aqui.
Okay. Thales, are you there?
Yeah, but for some reason I cannot start the video.
Oh, okay. Don't worry.
Yes. No idea. You cannot start your video because it's disabled by the host. Okay.
Oh, yeah, but I'm not the host.
Probably that, yes, Credo CVPF is the host.
Don't worry. So, the discussion was very short, Thales, and the banker decided to approve your thesis without any conditions. Let me be the first one to congratulate you. Thank you very much for your presentation. I think we saw all that you put a lot of work into your thesis. That was something that was done over the last 4 years. I want to thank the banker, everyone in the banker, for their time and their attention and the interesting discussion and valuable feedback. That was very great and very helpful for us and also for Thales. And yeah, Thales, congratulations and all the best for the future.
Thank you. Thank you for the support. Thank you for the opportunity to present this work. So I think I'm very grateful to it and looking forward to see what's next.
Next step. Congratulations, Thales.
Congratulations.
Thank you.
And thank you very much, Karsten, for the
No
invitation.
problem.
Good. As I think a big thanks for the both supervisor Carsten and Albert for the presentation of the analysis, for the development of the work, discussions, and a lot of things. I think it is me also to thank for Pa, which is one of the main also contributors of the analysis, was not part of this banca probably for some bureaucratic reasons, but also I think he also deserves a huge thanks for this work, and there is extra work too also that can be done in analysis, so this is quite interesting.
Okay, thank you, Thales. Thank you, everyone. I'm not sure the next step. I think Betsy will send around some documents for us to sign. Betsy, você vai mandar o documentos para nós?
Vou mandar tudo por e-mail, tudo explicadinho.
Tá bom, muito obrigado, Betsy. A
Nada.
gente está pronto.
Boa tarde a todos, então.
Obrigado.
Obrigado.
Okay, that's it.
Boa tarde.
Thank you very much, everyone.
Bye
Thank
bye.
you.
Congratulations. Thanks. Bye.
Obrigado.